Hi, EP students. In 9.3, we're going to talk about tests about a population mean. We just talked about population proportions, so it'll be pretty similar. So our conditions are still the same. We still want a random sample. Our normal condition is a little different. Remember, if it comes from a normal population, then our sampling distribution is normal. Or if n is greater than or equal to 30, remember, then by the central limit theorem, our sampling distribution will be approximately normal. Our independent condition is still the same. Either it's an independent sample or we follow our 10% condition, which is most of the time. So we have our batteries example. Remember, we had our mean battery life is 30 hours, and then we invented a new battery with a mean battery life that's greater than 30 hours, and we wanted to see if it was statistically significant. So below is a dot plot, a box plot, and a normal probability plot of the battery lifetimes for a simple random sample of 15 batteries. So the dot plot doesn't show us too much. The box plot shows no outliers, which is pretty good. And here's our normal probability plot. It looks pretty linear. It doesn't look too bad. We know that we have an SRS. And since n is only 15, we can't say that the sampling distribution is going to be approximately normal. However, if n is greater than or equal to 15, we have a new condition where we could say that if the sample shows no skewness or outliers, then we have the normal sampling distribution. Or here's another new one. If n is greater than or equal to 5, if our sample has a normal looking distribution, then that's okay as well. Because we're using a t-test which isn't quite as precise as the z-test. So we can have a little bit of error with these sort of things. So if we look at ours, remember our sample is 15, and I don't see any major skewness or outliers, so we could use that data. So we have our test statistic, we have our sample mean here, minus our population mean, divided by the standard deviation, right? S of x divided by square root of n. And then we'll have a p-value that's corresponding, and we use t-CDF in distributions, which is like our normal distribution for t. The battery company wants to test the null hypothesis mu, the mean battery life is 30, versus the alternative that the mean battery life is greater than 30, based on an SRS of 15 new AAA batteries with a mean lifetime of a sample mean x bar 33.9 hours and a standard deviation of 9.8. The test statistic is this. So we can actually find it. T equals 33.9 minus 30 over 9.8 over square root of 15. So 1.54, which is not a very large t value. In our t distribution, this is not that large. We'll go to Menu, Statistics, Distributions, and in our t distribution from 1.54129 to infinity with 14 degrees of freedom. And that's a 0.07, so that's close to being significant, but it's not. That's our p-value. Or we can run the whole test. So Menu, Statistics, Stat Tests, a t-test, and we are not given the data, we're given statistics. So our null hypothesis is 30. Our x bar was 33.9. Our standard deviation was 9.8. And our n was 15. Our alternative hypothesis was that our mu was greater than the null. And there we go. You can see there's the same t value, there's the same p value, There's the degrees of freedom, everything. Since our p-value, 0.072, is greater than 0.05, which was our alpha, we fail to reject the null hypothesis and cannot conclude that the mean battery life of the new AAAs is greater than the original. The level of dissolved oxygen in a river or stream is an important indicator of the water's ability to support aquatic life. A researcher measures the DO level at 15 randomly chosen locations along a stream. Here are the results in milligrams per liter. And there's our data. A dissolved oxygen level below 5 milligrams puts aquatic life at risk. Can we conclude that aquatic life in this stream is at risk, and we want to carry out a test at the alpha equals 0.05 level? So first of all, we need our null and alternative hypothesis. The null is that the mean DO level is 5. And our alternative is that the mean is less than 5. And you can see that we might be in danger. We see a 4 and a 3 and 4. There's 1, 6, but it looks like most of these are a little low. But where mu is the DO level, so we're going to run a one sample t-test for the mean DO level. We're going to check our conditions. We have randomly chosen locations, so we have a random sample. Our normal condition, n is greater than or equal to 15. So remember that means that we are looking at the distribution and we need it to not have any major skewness or outliers. So we need to put that data in our calculator. And now we want to look at the graphs. Well, that doesn't tell us much. So we don't see any major skewness or outliers by our dot plot. I very much like the dot plot for this, and it's very easy to draw because even though you did this on your calculator, you need to draw a picture. I'm not going to draw it very well right now, but with the scale and everything. So since no major skewness or outliers, the sampling distribution will be approximately normal. And independent, in this case, we could say that these 15 locations are independent of each other because the level at the one location will not affect the level at another location. So independent sample. Now I know I didn't give much space, but we're going to finish that test. Now we have data, so we can use our data. And our alternative is that mu is lower. So there we go. That's a pretty high p-value. So it looks like we had evidence to show that our DO level was a little low, but clearly there's not enough evidence. So we would need to write down our t, our p-value. I don't have the space for that right now. Basically, everything in this box needs to be written down somewhere when you do this, and I give you enough space. So we fail to reject. So it looks like the aquatic level life is not at risk because we did not conclude our alternative hypothesis. So given our conclusion in A, what kind of mistake could I have made? Well, this is a type 2 error since we failed to reject. Okay, type 1 is wrongly reject, and type 2 is wrongly fail to reject. We did not conclude that the life was at risk, but if we're wrong, life really is at risk. So that's a major error. So maybe a consequence of this is all the fish die, and that's a serious error. So in this case, a type 2 error is very bad. So here's another one. At the Hawaii Pineapple Company, managers are interested in the sizes of pineapples grown in the company's fields. Last year, the mean weight of the pineapples harvested from one large field was 31 ounces. A new irrigation system was installed in this field after the growing season. Managers wonder whether this change will affect the mean weight of future pineapples grown in the field. To find out, they select and weigh a random sample of 50 pineapples from this year's crop. The Minitab output below summarizes the data. So here's our data. We have our mean is 31.9, which is slightly larger than 31, and we want to determine if there are any outliers. So first of all, we have to do our 1.5 times the IQR rule. So we need and then we need this above the third quartile and below. So plus 34.115. So there's our threshold, and if our max or our min is outside of those, then we have outliers. So our minimum is not, and our maximum is not, so there are no outliers. Do these data suggest that the mean weight of pineapples produced in the field has changed this year? Give it appropriate statistical evidence to support your answer. So our null is going to be that our mu is 31, because that's what it originally was. And then we want to see if it's changed. So our alternative is that mu is not equal to 31. Well, we know we had a random sample. Our n was greater than or equal to 30 because it was 50. And we can assume that 50 is less than 10% of all pineapples. So it meets our independent condition. Then we need to run our test. We are given statistics, not data this time. Our mean was 31.935. Our standard deviation was 2.394. And we had 50. So our t is 2.76 and our p-value is 0.008. So can we conclude that the new irrigation system caused a change in the mean weight of pineapples produced? Yes. Since, and this is what you guys are going to forget, this yes. Remember, answer the question. 0.008 is less than 0.05, well, whatever alpha that we chose to use. Maybe we use 0.01, doesn't matter in this case. We reject the null and conclude that the mean weight of the pineapples differs from 31 this year. So here's the Minitab output for significance test and confidence interval based off the pineapple data. So our t and our p-value match, and it's a 95% confidence interval, and you see that 31 is not in that interval. So we get the same significance readings. So ignore that nose because it's not on yours. Researchers designed an experiment to study the effects of caffeine withdrawal. They recruited 11 volunteers who were diagnosed as being caffeine dependent to serve as subjects. Each subject was barred from caffeine, colas, and other substances with caffeine for the duration of the experiment. During one 2-day period, subjects took capsules containing their normal caffeine intake. During another 2-day period, they took placebos. The order in which the subjects took caffeine and the placebo was randomized. So some people were on the caffeine, some were on the placebo, and they swapped. At the end of the 2-day period, a test for depression was given to all 11 subjects. Researchers wanted to know whether being deprived of caffeine would lead to an increase in depression. So the table below contains the subjects' depression scores. Higher scores show more depression. So it looks like, just looking at this data, they are more depressed on this placebo than they were on the caffeine. So we're looking for a change, and this is a matched pairs test. Remember, matched pairs is when both treatments are given to each subject. So we want to look at the difference in depression. So if I want to subtract these, I can use my calculator to do all of this. So why did the researchers randomly assign the order in which the subjects received placebo and caffeine? Because with any matched pairs, order could affect it. People could just be grumpier over time or something like that. So they wanted to control for that. And we want to carry out a test. So I'm going to enter all these values in my calculator. And now I want to find the differences. So I'm going to set up a formula. I'm going to look for my variables. I'm going to say placebo minus caffeine. Now remember, looking at our data, it looked like the people with placebos had higher depression scores, so most of these are going to be positive. And you can see that looking at our data, they're all, except for this one, positive. So there's some strong evidence right there. So I want to look at my differences. And there's a box plot, no major skewness or outliers, and since we only had 11 subjects, it needs to look relatively normal, approximately normal. And looking at our normal probability plot, looks approximately normal. The points are pretty close to the line, so that's not bad. Now I'm glossing over the details, but we're running a one sample matched pairs t-test. And our null hypothesis is that our differences equal 0, and our alternative hypothesis is that our placebo had higher depression scores, so greater than 0, by the way that we subtracted. If we subtracted it the other way, we would have wanted less than 0. We had random assignment, so that satisfies our random condition. We checked our plot, and it looked approximately normal since n is greater than or equal to 5. And then our independence, 11, is less than 10%. Okay, I'm glossing over this to save some time. And now for our test. We have the data, so we'll use it. We're testing it, our differences against the 0, and we're saying it's greater. Higher depression. And there it is. Our t is 3.53, which is very high, and our p-value is 0.002. So we would say, since 0.002 is less than 0.01, or 0.05, whichever alpha we use, we reject the null hypothesis. We conclude that depression scores were higher when they were taking the placebo. So it looks like caffeine does lower depression. I'm not going to write all that because this is already too long of a video. So good luck. I know there's a lot, but it's not that bad.